let's work through an arc length problem here. We've got our vector valued function, and we need our formula, s of t. And we'll remember this is just the integral from a to b, the magnitude of r prime of t dt. And now we just need to find the magnitude of r prime. So first let's go r prime. Here's r prime of t is going to be equal to 12. I'll just go ahead and use our standard vector form here. And we're going to have 24 over 2, which is 12t to the 1/2. And for the k component, it's just going to be 6t. So there's r prime of t. And now we need its magnitude. That's going to be the square root of the sum of the squares of the individual components. So 144 plus 144t plus 36t squared. So there's our magnitude. And now we throw that into our integral here. So the integral from, in this case, we're going 0 to 1. We have our square root of 144 plus 144t plus 36t squared dt. And hopefully this simplifies, and it does because I've designed it to do that. If it didn't have a really nice antiderivative like it does, we would probably just go ahead and use a computer algebra system or one of our techniques of integration to help us through that. But this does actually work out pretty well. It turns out that this factors into 12 plus 6t quantity squared. So now we're taking the square root of a square, that cancels. So this whole thing then will just turn into the integral from 0 to 1 of 12 plus 6t dt. And obviously that's not a very challenging antiderivative. And go ahead and evaluate from 0 to 1. At the top end, it turns into 12 plus 3, which is equal to 15, and at 0, it's 0. So in this case, the arc length is just given as 15. Again, it worked out really well because it was designed to simplify down here. Not all problems will go quite that smooth. Again, if you encounter too much trouble, we have computer algebra systems, integral tables, and other techniques of integration that can help us solve those out.